Hello, this is Mrs. Hanson. How are you? Today we're going to look at the Chapter 16 KSP No Calc Practice. As always, I'm going to kind of roll through these, and I hope that you scroll to just the ones that you have questions on. I hope that I clarify some things and just answer some of your questions. But please, for heaven's sakes, just because I've explained it doesn't necessarily mean you understand it perfectly. So be sure to ask your teacher for clarifying questions. Okay, so let's go ahead and get started. So here's number one. Well, right off the bat, this is by far one of my favorite questions. So I would definitely make sure you put some stars by it. Okay, so it's basically a Q problem to the max. So let's take a look at it. It says that you have a 0.010 mole sample of potassium sulfate, which is a strong electrolyte. So that would break into K plus and SO42 minus 100%, is added to 1 liter each of two different solutions. One that contains barium nitrate, again, another strong electrolyte, would break up completely, and another one that contains silver nitrate, okay, another strong electrolyte. Which statement best describes what's observed? Okay, so basically, we have the potential of making two different precipitates, barium sulfate and silver sulfate. So we basically have to look at Q for both of them and decide which ones will precipitate. So we'll look at barium sulfate first. So we add this sulfate to the solution that contains these barium ions. And the question is, are the ion concentrations such that you're going to see a precipitate? So pretty easy. We don't really have any dilutions or anything like that because we just have this 1 liter solution. So this is 2.0 times 10 to the negative third molar for the barium. Okay, and for the sulfate, it's 0.01 moles, but it's in a 1 liter solution. So that's basically the molarity as well. So it looks something like this. All right, so 1 barium, 1 sulfate, so it's basically X times X more or less. So let's see what we get. Now, for doing this kind of mental math, I really like to use scientific notation. So I'm going to change that to 1.0 times 10 to the minus 2. So now it's really easy to multiply. So that's 2 times 10 to the negative fifth. Okay, well, that's Q, and here is K. So it looks like Q is much larger than K. So yes, we would see barium sulfate precipitate. All right, well, let's do the same exact thing, but this time for the Ag2SO4. So let's see, the Ag plus swimming around in this solution would be 2 times 10 to the minus third. Okay, but don't forget to square it, okay, because there's 2 of them. Okay, now no need to double it. So there's no reason to make this like 4 times 10 to the minus third because the silver and the sulfate are coming from different sources. So you just have to reflect the fact that there's 1 silver per every 1 nitrate here. So this number is good to go. And using the sulfate ion concentration again. All right, let's crunch some numbers. So this time I'm going to go ahead and square this first. So that would be 4 times 10 to the negative 6. And then multiply it by 1 times 10 to the negative 2. All right, looks like 4 times 10 to the minus 8. So as it turns out, that's Q, and K is times 10 to the minus fifth. So it looks like Q is less than K, so no precipitate of silver sulfate. All right, so I guess the net result here is the barium sulfate would precipitate because Q is greater than K, but the silver sulfate would not. And I would say A is the best description of that. All right, what do you think? So you definitely, there's no way around it. You had to do the calculations to validate that answer. All right, wonderful. Let's see, let's move on to number 2. So for number 2, it says, for which of the following can we directly compare the KSP values to determine the relative solubilities? So relative solubilities on an ice table would mean that we're solving for X. Okay, so the only time that we can just use K values instead of solving for X is if the compounds that we're comparing have the same number of ions. Okay, so for letter A here, see 2 Ags and a chromate. Okay, so that's 3 ions in total compared to 2 ions. So guess what? Can't compare their KSPs. You'd have to solve for X to decide which one's more soluble. B, let's see, 3 Ag, 2 Ags and a sulfate versus 2. Okay, so not comparable. 3 ions versus 2 ions, not comparable. So D is the correct answer. 2 ions each. So the higher the KSP value, that would mean the greater the X value, so the more soluble. All right. Pretty easy concept. We like those kind of questions. Good. So next in line, it looks like we're looking at number 3. It It says the salt, MX2, has a solubility, so that's basically an X value, of 1 times 10 to the minus fourth. Determine the Ksp for MX2. All right, so if you were thinking, I'll just set up the ice table for this one. Okay, so your ice table would look something like this. Okay, and basically you have some amount of precipitate, okay, and it's going to go in the forward direction. Okay, so it looks something like this. All right, so we're basically going to put these two guys, and we're going to make sure and square this, pop that into Ksp. So we're looking for Ksp, and we basically have X. All right, so that being said, we can go ahead and collapse that together into, let's see, 2 squared 4x squared times another x, 4x cubed. Okay, and let's go ahead and math this out. So 1.0 times 10 to the minus fourth cubed equals Ksp. All right, so 1 cubed, of course, is still 1. So it's 1 times 10 to the negative 12. Okay, and then times 4. So it looks like our Ksp value, if I can squeeze it in, 4 times 10 to the negative 12. Boom. Looks like our answer is D. So another really pretty easy one, but definitely relies on a little bit of mental math. Okay, so let's move on. Okay, so let me take a break. I'm in my classroom and my lights went out again. So I'm going to go turn my lights on. That'll probably happen like 2 or 3 more times. That's okay. So this one, it says 3 ionic salts. Okay, they all have different numbers of ions. Each have a solubility of 2 times 10 to the negative fifth. Which of the following correctly ranks the Ksp values? Okay, so this one, you basically kind of very similar to number 3, actually. So if you just visualize the ice table, this one would be x squared, okay, to get Ksp. Okay, this one here would be, let's see, 4x cubed, okay, if you can get to that. If not, it would look something like this, which would simplify to 4x cubed. And this one would be x and then 3x, right, because there's 3 x's per every c, and then cubed. So if I simplify that guy, okay, please don't forget that 3 cubed is not 9, okay, it is 27. Okay, and then x to the third times another x, x to the fourth. Okay, so we're doing this without a calculator, right? So this guy right here is our solubility, so that's more or less our x value. So it's basically, if you just deal with the exponents, like this, for instance, right here, let's see, 2 times 10 to the negative fifth squared, that's going to be on the order of 10 to the negative 10th. Okay, whereas this one is 4x cubed. Okay, so when you put that x value or that molar solubility in, this time you're cubing the exponent, so that's going to be on the order of 10 to the minus 15th. And this one is going to be on, you're basically, raising it to the fourth power. Okay, so that's going to be, 2 times 10 to the negative fifth raised to the fourth, so that's going to be on the order of 10 to the minus 20th. So I'm telling you, if you just really focus on how the exponents change, makes it so much easier. So as it turns out, it looks like this guy absolutely has the smallest Ksp value. So it's going to be the least, or just have the smallest Ksp value, which is what it's asking for. Okay, so it says from least to greatest. So it looks like we're going to list Cx third or 3 first. Okay, and then this guy next, and then this guy, just the x squared one is going to come through with the largest Ksp. Okay, so hopefully you guys see how that works, see sort of what the relationship is. Okay, so that's number 4. How does that sound? All right, sorry that was so messy. Sheesh. Okay, so let's see. Number 5. Ooh, a lot to read. It says aqueous solutions of sodium chloride and sodium chromate. By the way, these are both strong electrolytes, okay, meaning that they dissociate 100%, are mixed and they do not react. Okay, so we basically have this big beaker, okay, and you got all these Na pluses and Cl minuses, okay, and then you also have some more sodiums, okay, and then some dichromates, okay, and of course there'd be a lot more of these ions, but you get the idea. Okay, they do not react. To this mixture, an aqueous solution of silver nitrate is added dropwise. Okay, so basically we're going to come through, okay, and we're going to add some Ag plus, and NO3 minus, we're going to add it dropwise. Okay, and you can probably guess that the spectators here definitely would be nitrate. Okay, and all these silver ions, okay, they're basically just our spectators. Okay, so we're more or less just adding silver ions dropwise to the solution that has these chloride ions and this chromate. Okay, I'm like, what's going to happen? So it goes on to say, at first, a white solid forms. Okay, and as the Ag plus is continuing to be added, then a yellow solid begins to form. Okay, and then it goes on to say that AgCl is white. Okay, so what that means is that this guy must be the AgCl, and silver chromate is yellow. So the second guy must be the silver chromate. Okay, so basically, what does all that mean? All right, a couple things about some of these choices. The molar solubility of sodium chloride is greater than the molar solubility of sodium chromate. Well, I'll tell you what, absolutely nothing to do with anything, because both of these are strong electrolytes, so they dissociate 100%. Okay, so not the issue. Really, the same thing with B. The molar solubility of sodium chloride is less than the molar solubility. So guess what? It has nothing to do with it. Okay, so these definitely comes down to C and D. So it's basically, they basically say the same thing but opposite. The molar solubility of AgCl is greater, or the molar solubility of AgCl is less. Okay, well, what it boils down to is basically the colors. So the white solid forms first. So that means AgCl forms first. Okay, so when that silver is dropped in, it basically hooks up with the Cl and is making AgCl first. Okay, and guess what? You see that precipitate? So that means that it's not soluble, okay, because you're seeing the precipitate first. Okay, and then after some time, okay, then all of a sudden you keep adding Ag plus, raising the ion concentration, and then secondary, then you see the silver chromate. Okay, so the bottom line is the fact that you see this guy first means it's actually less soluble. Okay, so that means the best answer choice there would be D. The molar solubility of AgCl is less than the molar solubility of this guy because the white solid, meaning the silver chloride, came out of solution first. Okay, so kind of a unique question, a little bit different than what we've seen, but hopefully that makes sense. Okay, all right, bottom line is the more readily, the more quickly that you see the precipitate, that's because it's not soluble, it's less soluble. All right, good news. Okay, moving right along. That was number 5. Let's see. Ooh, I really like number 6. Okay, so number 6 says barium iodate. First of all, might start by figuring out what that formula is. So barium is a 2+ ion, and iodate is kind of like chlorate. Okay. Okay, and chlorate is actually ClO3. So iodate is IO3. Okay, minus. So take home message, how many iodates would you need to balance out that barium? So the formula looks something like this. Okay, the Ksp is 4 times 10 to the negative 9th. What is the iodate ion concentration? Okay, so a lot of the previous problems, we did exactly the opposite. I gave you the X value. You had to come up with the Ksp. So this one, I gave you the Ksp. We need the X value. Okay, so let's go ahead and do that. So we got Ksp, and then if we visualize the ice table, barium is X. The iodate would be 2X, and then we'll square it. All right, so what we're looking at here is 4.0 times 10 to the negative 9th. And then your classic 4x cubed. Okay, so we'll divide both sides by 4. Okay, and that gives us 1 times 10 to the negative 9th equals x cubed. Go ahead and take the cube root. Life is going pretty good. I like that. And it comes out to 1 times 10 to the minus third. So when you take the cube root, you just divide it by 3, or take a third. All right, so unfortunately, a lot of you are probably tempted to pick A, but guess what? A is not the right answer. So please remember that X is not what it's asking for. It's not asking for the molar solubility. Okay, it's actually asking for the iodate ion concentration. So if you think back to your ice table, if this guy's X, the iodate is 2X. So that's what I'm looking for. So your actual answer is this number, but doubled. So that's why D is the correct answer. So tricky. All right. That's a good one. That's a good one. Just got to read the question carefully. Make sure you actually answer what it's asking. Okay. Number 7. Ooh, this one, really good one. says which of these salts would have increased solubility in a 0.1 molar nitric acid solution. So it's basically saying which of these salts would be more soluble in acidic conditions. So I would say you want to look for two things. Look for OH minus being present in the salt, and then your conjugate bases of weak acids. Okay, so let's take a look. So we got AgBr. So basically, the cation is not the issue. Okay, so we're just looking at the anions here. So we got Br minus. Well, that's a conjugate base of a strong acid. So what that means is that Br minus has no interest in hooking onto that H plus from this acid solution. So AgBr would be equally insoluble in water as it would be in an acid solution. So not the right answer. Same thing with B, because you have that chloride, also a conjugate base of a strong acid. So it's just not going to be affected by pH. Same thing with D, because this one has the I minus. So it looks like our winner is MgOH2. Thinking about that equilibrium, okay, it would look something like this. Okay, and when you add that H plus from this acid lowering the pH, it's going to interact with the OH minus. Okay, that's going to lower the OH minus, and it's going to shift the equilibrium forward. Okay, and by the way, I should probably finish that this turns it, the OH minus reacts with the H plus to make water. Okay, so then it's going to become more soluble. All right, so again, take home message, make sure you look for salts that have OH minus and conjugate bases of weak acids. They will be more soluble in acidic conditions. Okay, so they're affected by pH. Good. All right, so that's a good one. Let's see, what's next? Okay, number 8. 8, another nice little calculation. It says when 0.1 moles of solid silver oxalate is added to 1 liter of pure water, a saturated solution results. The solubility of Ag2C2O4 is blah, blah, blah. What is Ksp? So again, I gave you the X value. Okay, we're looking for the Ksp. Okay, so for this guy, let's see, it would be 2X for the 2 silvers, X for the oxalate. Make sure you square the silver. So another 4x cubed. All right, so let's go ahead and solve that. Okay, so we'll put in 2 times 10 to the minus 4th, and we'll go ahead and cube that. All right, so let's see, 2 times 2 times 2, 8 times 10 to the negative 12, and then we're going to multiply it by 4. So it looks like we're going to get 32 times 10 to the negative 12. All right, so if you go ahead and move it from 32 to 3.2, then we'll change this to minus 11. Okay, so it looks like C is the closest answer. All right, so good. Hopefully you guys are getting really good with this type of question. All right, number 9. Okay, so basically says 10 grams of calcium. This one's just like a little experiment. You got to make sure you visualize it. 10 grams of calcium hydroxide is added with stirring to 100 mils of water, producing a saturated solution with solid calcium hydroxide on the bottom of the beaker. Okay, so bottom line, what I see being described here, okay, is it was a saturated solution. Okay, and you're absolutely certain about it because even though you keep trying, you can't get any more of the precipitate to dissolve. So this system is definitely at equilibrium. Okay, so let's go through the choices. So adding acid will cause Ksp will not change Ksp. So the only thing that ever is going to change Ksp is temperature. Okay. B, the addition of more calcium nitrate will cause some additional calcium hydroxide to form. Okay, so if we look at the equilibrium here, looks something like this. Okay, and I would say this is your classic common ion effect. So you're basically adding some calcium ions, so that's going to cause the equilibrium to shift this way. Okay, so yes, it will cause you to generate some more precipitate. So B is true. Just for the fun of it, let's look at the other ones too. Okay, the addition of 0.1 moles of solid NaOH will cause some additional calcium hydroxide to dissolve. Okay, so that's exact. And by the way, interestingly enough, they use the word solid here, which pay no attention to that because both of these are strong electrolytes. So even though they're being added as solids, as soon as they hit that aqueous media, they will dissociate. So this is basically a source of calcium ions, and this is basically a source of hydroxide ions, okay, with the sodium and the nitrate being spectators. Okay, so this one, common ion effect as well, but you're increasing the OH minus, so it would also shift backwards and make more precipitate, but it's saying right here the exact opposite, that calcium hydroxide would dissolve. So C, not true. D, the addition of 0.1 moles of solid calcium hydroxide would cause Ksp to change. Nothing's going to change Ksp. All right, so really good conceptual question. All right. Whew, we thought 9 was wordy. Let's look at number 10. So this one, whole long story. I'm going to take a drink of water. All right, it says solid sodium chloride was added to water slowly with stirring at 25 degrees until no more sodium chloride will dissolve. So that to me means a saturated solution, means equilibrium. Okay, good. Solid remains on the bottom of the container even after the solution was stirred. So it's really just taking the message home that this is a saturated solution, it's at equilibrium. After the solid was allowed to settle, some of the clear, colorless solution was carefully poured off the flask. So basically, we collected this saturated solution. All right, here's where it gets interesting. The flask was placed in the refrigerator, okay, and lowered to 4 degrees. When the flask was removed from the refrigerator, a small amount of white solid was found to have appeared. Okay, so let's catch up here. So we're dealing with sodium chloride solid, breaking up into Na plus and Cl minus. Okay, we had this perfectly saturated solution, okay, that we had filtered, so it looked like water, okay, salt water, in fact. But then we lowered the temp and some white solid was formed. So the fact that some white solid was formed means that as temperature went down, okay, the equilibrium shifted this way, okay, because we were seeing the production of white solid. So what does that mean? Okay, solids settle out of the solution over time. I wouldn't say that can happen, okay, but that's really more of a phenomenon of the equilibrium shift. NaCl has an exothermic heat of solution. Okay, well, let's see what happens here. So as temperature decreases, it shifts this way. So I would say that the energy has to be on this side, meaning endothermic, okay, because when the temperature decreases, that would indeed cause the equilibrium to shift this way to replenish that. Okay, so in fact, it's not exothermic, it's endothermic. Okay, and heat of solution implies like the energy needed to basically dissolve this. So heat of solution is another way to describe this dissolving process. Okay, the Ksp of NaCl decreases with decreasing temperature. Okay, and I would say that is absolutely true because that's what we're describing here. Okay, as temperature went down, Ksp did decrease because it did go in the backward direction. Okay, so you remember large K means you go forward, smaller K means you go backwards. Okay, and finally, just to make sure, the molar solubility of NaCl increases with decreasing temperature. So that's false as well, because when you decrease the temperature, the molar solubility actually decreased because it was going backwards. Okay, so I would say C is the best answer. What do you think? All right. Hopefully that clarifies that one, but again, be sure to ask your teacher if it doesn't. Okay, so let's go on. Number 11. It says here, which of the following I like this one. I like this one a lot. It says, which of the following statements is true concerning the relative solubility of silver chloride? All right, so I'm going to go ahead and wrap myself a nice little equilibrium. Okay, and it says AgCl is less soluble in silver nitrate. Okay, so if I take a look at that, if this guy goes up, okay, then the equilibrium would shift this way, which does mean less soluble. Okay, so that's the presence of the common ion, Ag+. So far, A is correct. Let's look at the other choices, though. B, AgCl is less soluble in an acid solution. Okay, so would AgCl be one of those salts that's more acidic in low pH or in the presence of H+? Okay, and the answer is no, because this is a conjugate base of a strong acid. So this not a good conjugate base, so it would not be inclined to grab that H. So this reaction would not happen. Okay, so if it's not happening, guess what? Solubility of AgCl will be unaffected by low pH or the presence of acid. So not true. AgCl is more soluble in silver nitrate. Okay, well, that's exactly the opposite. Let me just go ahead. Whoops, let me make this a little smaller. Whoop, try not to make a mess. Okay, so this one, basically silver nitrate, if this went up, of course, we know it's going to go backwards. So that's the exact opposite of letter C or letter A. And then finally, same thing right here. This would be unaffected. Okay, so A is the best answer. All right, good. So that's a good one. Let's see what else we have. Number 12. It says the molar solubility of a hypothetical metallic hydroxide, MOH2, is blah, blah, blah. What is the pH of the saturated solution? Okay, so with this one, number 12, okay, a quick calculation. So it would say that the molar solubility, so this guy is basically X. Okay, but if you think about it, with your MOH2, if you visualize the ice table, this guy's X, this guy would be 2X. Okay, so what that means is that you're going to have to double this. So that's going to be 2 times 10 to the minus 2 would be the molarity of the OH minus. Oops, I'm having trouble writing here. Sorry. Okay, so I think that's the key right here is just remember that when we talk about molar solubility, okay, that's the solubility of the whole compound. Okay, so that's equal to X. But when you're looking at a specific ion, okay, you have to take into account stoichiometry. Okay, so 2X for the hydroxide. All right, so that being said, now we can go ahead and get the pOH by taking the negative log of that. Okay, and bottom line is, guess what? I would say the answer is definitely going to have to be D, because when you take the negative log of 2 times 10 to the negative 2, okay, well, you remember if you take the exponent 2, it's going to be in 1 pH unit below. So it's going to be something like 1.8 or something like that. Okay, so if that's the pOH, then when you get the pH, that's 14 minus 1.8. Okay, so it's going to be like 12.3. Okay, it certainly can't be 12.0. Okay, and these two don't make any sense because, of course, they're acidic. Okay, so it's going to have to be more basic, basically more basic than 1.0 times 10 to the negative 2. Okay, if it was this number, then that would be a pOH of 2. Okay, and that would be a pH of 12. So it's basically like C is absolutely not the right answer. So with a little more, because there's double the amount of OH, that's why it has to be D. Okay, so hopefully that's a good little shortcut. All right, let's see. So next one, number 13. All right, so basically number 13 is looking at two equilibrium expressions. So we got NaCl breaking up, really large K value because NaCl is a strong electrolyte, it's pretty soluble. And then this guy, not very soluble, so its Ksp value is really small. So what's basically the difference between these two? Okay, so the best one, and I'm going to have to turn my light on again. Let's take a look at these choices. I'm back. The Ksp of silver chloride is so small that AgCl is completely insoluble. That is a dangerous word. So A is not true. It's not very soluble, but it's a little soluble. The Ksp of NaCl is so large that the reaction is not reversible. Well, guess what? All reactions are pretty much reversible. Okay, and with NaCl, the forward reaction is favored. Okay, I like this. The relatively large equilibrium constant tells us that products are favored. Totally can get on board with that one. Letter D, with silver chloride, the forward reaction is favored. That is not true, okay, because in fact, the backward reaction will be favored. Okay, so C is the best answer. Good. All right, number 14 it says the mineral fluorite is the main source of calcium fluoride. Calcium fluoride has a solubility of 2.2 times 10 to the negative fourth in pure water. Which is a correct explanation for what occurs when solid calcium fluoride is dissolved in acidic solution rather than pure water? All right, so let's take a look at that. So our solubility looks something like this. Okay, and it's basically asking, gosh, is this particular salt affected by low pH? Okay, so when I go ahead and have all that extra H plus, okay, well, in fact, this guy is a conjugate base of a weak acid, so the F will readily grab that H plus to make HF, and this is favorable. So that being said, by doing this process, you're going to lower the F minus, and this precipitate is going to go in the forward direction. So that means more soluble. So the best answer to explain that, I would say, is probably the solubility increases because HF is a weak acid. Okay, I can get on board with that. Certainly not a strong acid, and the solubility doesn't decrease. Okay, so A is the best answer. We are on the home stretch. So let's look at number 15. Whew, another one that's kind of wordy, right? So it says aqueous solutions of sodium carbonate and calcium nitrate, again, two strong electrolytes, 0.1 molar each, are combined. Okay, so let's do that first. So we would react these two puppies, and I'm sniffing out the potential of a precipitate here. So we'd make sodium nitrate and then calcium carbonate. Okay, and that would be the precipitate there. Okay, and you could go ahead and balance that, but I don't think it's really important. Okay, so it says a white precipitate is observed. Yes, I agree. Okay, the precipitate is filtered and carefully rinsed. Okay, so we're just basically going to have this calcium carbonate sitting there. A sample of the precipitate is added to 100 mils of water. All right, fair enough. Okay, being a precipitate, it's going to dissolve a little bit, but not very much. Okay, and the sample of the precipitate is added to 100 mils of sodium chloride. Okay, a second sample is added to HCl. Okay, so basically, if we add it to the solution of sodium chloride, boy, Na plus or Cl minus, or either of these ions really going to interact with either of the active players. Okay, so calcium 2 plus would make calcium chloride, but that's just a strong electrolyte, so it'd just be a bunch of ions. Sodium and carbonate would just make sodium carbonate, which is also a strong electrolyte, so a bunch of ions. So I would say adding it to the NaCl is just going to have no effect. Okay, a second sample of the precipitate is added to HCl. Oh, okay, different story. Okay, so a couple things about that. First of all, carbonate is a conjugate base of a weak acid. Okay, so of course, H plus plus CO3 2 minus would make HCO3 minus. Okay, so that would lower this. Let me use a different color here. That would lower this and it would shift it forward. Okay, that wasn't really a different color, was it? But there's a little bit more to it. I want you guys to remember that carbonates plus acids, do you guys remember what they make? They make a salt plus water plus CO2 gas. So bottom line, this is like the volcano reaction. So you would see all kinds of fizzing in the presence of carbon dioxide gas. So let's see what set of conditions fits best. So it looks like letter B, no visible reaction would occur when we added the sodium chloride. So this guy's out, this guy's out. And then it says gas is produced and some precipitate dissolves. So I would say B is a match because you would make the CO2, but just the same, you are also lowering the CO2 or CO3 2 minus ion concentration. So it definitely would cause the precipitate to dissolve. Okay, so B, all that reading and all that description, B is definitely the right answer. All right, the last one. Woohoo! So it says arrange the hydroxides from least soluble to most soluble based on their Ksps. So basically, we're asking for you to solve for X. Okay, that being said, of course, this guy's K value is very large. So I'd have to say that this guy's going to be definitely most soluble. Okay, and it says from least to most. So that means we're going to have to end with KOH. So that means these two choices are out. Okay, and then between these, it's sort of like, let's see, got 3 ions. So that's your 4x cubed situation. This one has 4 ions. So that's basically your 27x to the 4th. Okay, so let's see. If we go ahead and cube root this guy, so divide by 3, that's going to be on the order of 10 to the minus 2-ish. Okay, and this guy is going to be 4th rooted, if you will. So if we divide that by 4, okay, that's going to be on the order of 10 to the minus 8 point something. Okay, so long story short is I would say this guy is definitely way more soluble than this guy. So that means the correct order looks like it's going to be letter C. Okay. Well, I think that's it. Again, thank you for listening. Good luck with the KSP Twiz. And be sure to talk to your teacher if you have any questions. All right, signing off.